Okay, let's continue. So, before the break, we started to see how to make op amp. Again, started with a single transistor, built all the way up to the 5 transistor OT, and looked other ways to increase the DC gain. And then we saw that with single stage, all the OTS we have seen so far, they are single stage OTS. And what is one limitation with single stage OTA? It cannot drive resistive load. So that made us move on to a multi-stage structure like this. And when we had a multi-stage high gain op amp, we saw that the DC operating point as such is not properly defined. We need to have a DC negative feedback around it to set the operating point. And either ways, we want to have an op amp so that we can use it in negative feedback system. So we decided to see what happens when we put the op amps in negative feedback. So we started with a first order system like this. So here we notice that if we have a first order system, if I put it in negative feedback, so loop gain is what is defined as the gain you see when we go through the loop. So the idea is you null the excitations, break the loop somewhere, apply an excitation and see what returns back. And as I mentioned, in circuits you try to break it at a point where the impedance is high so that the loading is not disturbed. And in particular, we notice that the first order system, if I put it in negative feedback, it is guaranteed to be stable. And we also recognize that the unity loop gain frequency, that is a frequency at which the magnitude of the loop gain becomes unity, that exactly equals the closed loop 3 dB bandwidth, which is the feedback factor times the DC gain times the pole you have. Right? So that is with the first order system. So we know this is nicely stable. But now we are not interested in first order systems because we won't have multi-stage OTAs. So let's see what is going to happen with higher order systems. And remember, this is a closed loop transfer function. It is some 1 by beta times the loop gain by 1 plus loop gain of s. Now what is the, if I give a transfer function, what is the check you will make to see if it is stable or unstable? Pole should be where? Left half of S plane. So of course, if it's a first order system, we directly substituted the loop gain. It was easy to do. Maybe if second order system, maybe you can calculate. Third order system, again, it will just go out of our hands, right? So that's why we have techniques to make comments about the closed loop stability just by looking at the loop gain, right? And what are the techniques that you know? Maybe you learned it in control systems. Root locus, what else? Yeah, Nyquist plot. So Nyquist plot is there. Root locus is there. The most simplistic thing, the Bode plot, right? And the way I see it is, this is the increasing order of complexity, right? So, and root locus and Nyquist plot give exact information about closed loop stability. So we typically try to understand stability from either of these, and then translate that understanding to Bode plot because it is much easier to plot Bode plots. Right? Although traditionally this is done with Nyquist plot, I usually take an alternate approach and prefer root locus because if I were to explain Nyquist plot, I should explain complex analysis, Riemann zeta function, Cauchy's integral, number of encirclement this side, that side. So I'll skip all of that, and let's see how we can understand through root locus. And as we'll see, this is very intuitive to actually plot. Okay? Again, this lecture is not intended to make you understand how to plot root locus. At the end of the discussion, if you're still not, if you're not able to plot root locus, completely fine. That's not the goal. The final takeaway should be the key points that we derive from the root locus explanation. Okay. So again, just to do it, let me just quickly explain. So we are looking at the closed loop poles, which is the roots of this polynomial, 1 plus loop gain of s to be 0. So this is the polynomial. And if I were to write it, this is basically a DC gain times a numerator polynomial by denominator polynomial. This in turn I can write it like this. I'll even say the beta closed loop factor. Let's say. And root locus essentially sketches the roots of this polynomial as you vary one of the parameters, and that typically is the DC gain A0, right? So basically, are trying to plot the trajectory of closed loop poles as you change the DC gain A0. That's the whole idea. And I mean, we can make one quick observation, right? So let us say you make the DC gain to be 0. So in this equation, A0 to 0. So the closed loop poles become the roots of this equation, d of s equal to 0. The roots of d of s equal to 0, what does it imply? They're poles of what system? Open loop system. Remember, this is the open loop transfer function. Finding the roots of d of s equal to 0, that's simply saying I'm taking the open loop poles. So I'll say the closed loop poles start from is equal to open loop poles when the DC gain is 0. Similarly, when I make it infinity, so here A0 is infinitely large. So what term will dominate? This will dominate. So essentially, we are trying to find the roots of n of s equal to 0. The roots of n of s equal to 0, what does it tell you? Zeros of open loop, right? So basically open loop. So this directly gives you one quick basic principle that the closed loop poles start from the location of open loop poles, and as you increase the DC gain, it eventually reaches the open loop zeros. This is the main thing that we will use to qualitatively sketch root locus. And the second principle, second thing that we will use, I will not derive for the sake of time, but it's pretty trivial to derive. Remember that we are trying to plot the location of closed loop poles. So in general, it can be complex. Correct. So this locus, which is basically the locus of this closed loop poles, can either be on the real axis or on the S plane. It turns out if it has to be on the real axis, the condition is it should have, anyone remembers? On real axis, if there should be closed loop poles, what is the condition? Anyone remembers? It turns out there should be odd number of poles and zeros to the right. It is pretty trivial to derive. I'm just skipping for the sake of time. Because it turns out the phase has to be minus 180, you can actually easily derive it. So we'll just use only these two ideas and qualitatively sketch root locus and try to derive some understanding on stability. That's the whole focus. So let's start with a simple case, first order system. So as we know, the root locus starts from open loop poles and terminate at open loop zeros. So this is the open loop pole. Where is the zero here? Infinity. So basically it has to start from here and go to infinity. It can go to infinity on real axis or on in the complex S plane. Let's try to see what portion can lie on real axis. Again, for the plot to lie on the real axis, we should have odd number of poles and zeros to the right, and which means in this region I have odd number of pole. So basically I can have the root locus here. That's it. So which means this goes to infinity along this line. So this is how the root locus for a first order system looks like. And obviously now it is clear that a first order system, for any value of DC gain, the closed loop pole is in the left half of S plane, and in particular on the real axis, so it's definitely stable. No confusion. Again, reiterating the same thing. So first order systems are not interesting. Let's move to second order. So now I have two poles. So again, root locus starts from these 2 points, and where should they terminate at? Again, they should terminate at zeros. Where are the zeros here? Infinity. So they should go to infinity. Again, it should go to infinity. It can go to infinity either on the real axis or in the S plane. Let's figure out the portion on the real axis. Can I have a root locus plot here? So I can only have here. Correct. So which means as you keep increasing the DC gain, one pole starts to move this way. Other pole starts to move this way. Now, of course, they have to terminate at infinity. If it cannot go on the real axis, where can it go? In the S plane. Again, I have whole 360 degrees of S plane. So the logical thing to do is one takes the top half, other takes the bottom half. So now tell me, can a second order system become unstable? No, because the closed loop poles still lie on the real axis. So truly second order system, for any value of DC gain is still going to be stable, right? But as we see, if we have a large DC gain, the poles will lie on the complex S plane, right? So I'm showing here. So which means you will have poles of the form minus sigma naught plus or minus some j omega naught. So which means anytime I have a disturbance or a step input applied to this closed loop system, how will the time domain response look like? Remember that I have a closed loop pole which is of this form. So the time domain response, how should it behave like? Should be sinusoidal like this, truly? Not completely, so it should stop like this. Yeah, I mean, will it stop abruptly like this or what? What do you say? Yeah, I mean, remember that, see, anytime you have a pole P1 in your system, it means that your time domain response will have a component which is e power P1 times t, correct? So here you have e power this term, so you'll have a sinusoidal ringing, right? Now this part corresponds to omega naught, the sinusoidal frequency, whereas this decay corresponds to e power minus sigma naught t. So the time domain should contain e power minus sigma naught plus or minus j omega naught t, correct? There should be a component in the time domain response. So yeah, here again we can make a remark that now you see that if you apply any step and if you apply any disturbance in the system, in principle you can have a lot of ringing like this if the poles lie here. So if you do not want any kind of ringing in your closed loop response, in time domain response, where should you want the closed loop poles to lie? On the real axis. You don't want them on the complex plane. So that is one remark we'll make, that let me write it here. So closed loop poles, you want it on real axis to avoid ringing. Right? So now we have only looked at poles. So let's also introduce zeros. L zeros will feel left out. Let me see if I can copy the earlier thing here. Yeah, okay, nice. So I've taken the same second order system, but I've introduced an additional zero here. So as usual, the root locus will start from these two poles, and one of them should terminate at this zero, other should terminate at infinity. So let's figure out the portion on real axis. Can I have something here? I mean, I should have odd number of poles and zeros. Okay, so I have how many poles and zeros to the right here? 3. 3 is odd or even? Odd. Okay, hopefully that is not confusing. I can have something here. Can I have something here? No, I can have even number of poles. So which means I can have only here. Right? Again, the way to think of it is this, right? See, let us say you didn't have the zero at all. It was, let us say, at infinity large frequencies. The closed loop poles would have started here and would have gone like this. But now it cannot get lost in the S plane forever, because I know one of them has to terminate at this point, other should go to infinity, and it should go to infinity here, correct? So then what is the logical thing? So it cannot go here like this. What should happen? It should somehow bend, and one of them should go here, other should go here. That's the only logical thing. Let's not worry about what this point is, and all. I mean, that is for control systems people to worry. We just want a qualitative sketch of what's going to happen. So now tell me, if I introduce an LHP 0, do you think we are doing better than what we were before, or are we doing worse? Why? Yeah, now you see with the introduction of the left half plane 0, our poles, closed loop poles for large values of DC gain, they are falling back on the real axis. So which means we will not have a lot of ringing in the response. So in a way, I will say LHP 0 is good for stability. So now of course we see that with second order it is not stable. I mean it is always stable. Let's try to make it unstable. So let me introduce one more pole like this. So now we have 3 poles. Again, as usual, the root locus will start from these points and should go to infinity. Let's figure out the portion on the real axis. So can I have the root locus lying here? I can have here. So which means I can have only here. Then, and I know for a fact that the root closed loop pole should terminate to infinity. I see one of them is already going to infinity along this line. Correct. So which means I should figure out what happens to the other two. And I mean it's pretty logical. I have 3 of them. I have entire 360-degree of plane. So what will I do? I divide them equally. Simple land division problem. 3 kids are there. You want to divide the ancestral property 1/3, 1/3, 1/3. Right? So same thing you do. I'll say 120 degrees for this fellow, 120 degrees for this fellow. So now, do you think a third order system can be unstable? Yeah. You see that for any DC gain greater than this point, I'll call it A0 prime. For A0, the DC gain, if you make it greater than A0 prime, this easily becomes unstable. Now note that if this DC gain A0 prime is really large, say 1 million or 10 million, then we are at least okay, right? Because at least till 1 million DC gain we are okay. But it turns out this value is very small. I'll give it in the practice problem. So that's why this is a problem. So let's just do one last plot and then we can start making remarks. So now I have taken another third order system, 3 poles, but I've introduced 2 additional zeros. Right? So let's see what's going to happen. Let me just make some space here. So as usual, root locus starts on these points and 2 of them should terminate at these 2 zeros. Other one should go to infinity. So again, the way to see is this. Okay, let's plot the portion on the real axis, right? So can I have something here? I can have here. So which means every alternating point I'll have. Again, the way to see is assume that the zeros were not there, they were at infinity, which means the closed loop poles were doing something like this before. Now, if the zeros were not there, they would have actually gone like this. So now what will happen? You see, one of them is already getting terminated here. That is clean. The other one should get terminated to this 0. The other one should go to infinity here. So the only logical thing is after some point this should basically fall back. One of them should go here, other should go here. Now note that if the zeros here were at very large frequencies, this can actually be in the RHP for a long time and then it will take time to come. And if the zeros are very close by, it might not even enter RHP, it will just do this. Right? Now I've taken a middle ground where I assume that for a small time it is still in the RHP. So as you see, when you didn't have any zeros, the poles were going kind of crazy into the RHP. But the moment you have poles, the poles are acting like a magnet and attracting the poles to fall back on the real axis. So the lame analogy I give is, poles are like naughty kids. There are a lot of naughty children at home. They go all crazy, play, break all things at the home. But if you have 2 strict parents, then they'll be disciplined and fall back in line. Right? Same thing happens. Cool. So now let's use this and try to make some sense about stability. Again, as I mentioned, it's not practical to plot root locus for every system. So let's try to map this understanding to Bode plot. So I've sketched the Bode plot here. Again, you don't have to take full notes, just listen to me, it's enough. The final takeaway is what is important. So I'll have the root locus also to the side. So on the right side, I basically sketched the rough Bode plot for the same system. So you can see I have 3 poles. After 3 poles, what will happen to the slope here? minus 60 dB per decade, and then I have two zeros. So what will happen to the slope here? Minus 20 dB per decade, and this is the phase plot. Roughly I've sketched it. When I have only one pole, the phase starts from what value and ends at what value? 0 to plus 90 minus 90 minus 90. I have three poles, so phase will go to what value? So it seems like it's trying to go to minus 270. But then I have two zeros, left half plane zeros. When I have one left half plane zero, what will happen to the phase? It will go to plus 90. I have two of them. It will increase to plus 180. So minus 270 plus 180. It tends to go to minus 90. This is just a qualitative sketch. Okay, I mean, don't exactly try to see what happens here. Okay, so now let's actually look at this DC gain A0 prime. Remember, I start with very small values of DC gain, the poles are here. As I keep increasing, they kind of branch out like this, and at some particular value, the poles are lying here. Correct? At A0 equal to A0 prime, what can you say about the closed loop poles? I mean, forget about marginally stable. What can you say about the closed loop poles? Can you make any comment about the location of the closed loop poles? They are on what? Yeah. At this value of DC gain, the closed loop poles are exactly on the j omega axis. Two of them are at least on j omega axis, right? So which means technically I should be looking at the roots of this equation, 1 plus loop gain equal to 0. And the roots in general can be a complex number. But for this value of A0 prime, it turns out even if you substitute S as j omega, you can actually make it go to 0. Right? That is, the roots of this equation is truly imaginary. At least two roots are truly imaginary when you choose this value of A0. That's what I'm trying to say. Is it fine? So which means now we can do this. So now we can rewrite this. This is basically loop gain of j omega equal to minus 1. So what can you say about the magnitude of the loop gain now? What can you say about the phase at this frequency? So let us now try to, I mean, first of all, but before that, why am I interested in this value of A0? Yeah, after this point, you see that the poles are entering RHP. It is kind of setting a limit for me as to what is the gain. Right? That's why I'm looking at this. Let us translate this A0 prime here. Right? That is, here I have sketched the loop gain value for some DC gain A0 hat. Now I'm going to change the DC gain so that I am drawing the Bode plot corresponding to this value. Is that okay? If I change the DC gain, what will happen to the magnitude plot? These are all in dB. If I change the DC gain, what will happen to the loop gain's magnitude plot? In DC, I mean, since I am plotting in decibels, it is going to shift up or down. What will happen to the phase plot? It will be same. It's just a scaling factor. Phase doesn't get affected. Phase will remain the same and magnitude will get changed. Right? So think of it like this. Only magnitude is going to change. Let's assume that I'm starting with a very, very small value of DC gain. So maybe the plot is somewhere like this. The same plot will get shifted down. I mean, something like this. Now I'm increasing the DC gain. As I keep increasing DC gain, when I reach this value of A0 prime, I see that when the magnitude is 1, phase is minus 180. So basically phase is minus 180 at this point. So if I keep shifting the magnitude, I should come to a point where at this frequency, magnitude is 1. Again, this is 0 dB. Correct? That's how I'll find out that's how I'll figure out if I've gotten the correct DC gain A0, right? So you don't have to do, I've done this already. So let me just show you. Just a representative figure. Oops. Yeah. So this is A0 hat, this is 0 dB. So here is where I have basically scaled down the plot. So this corresponds to a DC gain of beta A0 prime. So here you see when the phase is 180, gain is 1. Okay. Now let's say that I keep increasing the DC gain further, right? And then I hit this point, A0 double prime. Even at this value of the DC gain A0 double prime, what can you say about the closed loop poles? They are, even for this value, they are on j omega axis. So which means even if I choose this value of DC gain, I'll have the same condition. Correct? So which means now you see that the phase is going to minus 180 again at this point. So if I keep shifting the Bode plot, at some point I'll have this crossing here. Okay. So I've drawn that also. You don't have to draw it. So here is where I have. Okay. So I kept increasing the DC gain. I find that at this point, when the phase is 180, the magnitude has become 0 dB. So this I'll call it as beta A0 double prime. And again, why is this point relevant for me? Why am I looking at this value of DC gain A0 double prime? After that, the system is stable. So the danger region is between A0 prime and A0 double prime. Correct? So which means any DC gain I have between A0 prime and A0 double prime will result in a corresponding magnitude plot somewhere here, right? So this is going to be my unstable region. So which means if I have any DC gain in this range, the corresponding magnitude plot in Bode plot will lie somewhere here. It's okay. So which means now if I have to sense if the system is stable or not, I just have to check if the magnitude plot is lying in this region. That's all I have to do. Right? And tell me, how did I first conclude that this corresponds to a DC gain of A0 prime? How did I sketch this? I looked at the phase where it is minus 180. When the phase is minus 180, the gain is 0 dB. Same thing for this also. Correct? So which means these are the edges for me, right? A0 prime and A0 double prime are the edges for me. Below this or after this I am safe. In between is where I am unstable. And I also know that I figured out A0 prime by looking at the phase and checking the magnitude, right? So which means if I have any Bode plot in this danger region, so let us say I have some Bode plot here. If I look at the phase when the magnitude becomes 1 or 0 dB, what can you say about the phase? It will be more than 180. Absolute value is more than 180. Okay. So that's how we can basically map the understanding that this is going to be my unstable region, and I have decided on the boundaries based on this fact that when the phase is minus 180, my magnitude is 1, or when the magnitude is 1, I am checking what is the phase. Correct? So which means any unstable Bode plot will have a phase which is greater than 180 when the magnitude is 1. So that's what I have to do. So let me remark it here. I'll check the absolute value of phase to avoid the negative confusions. And remember, I'm looking at the frequency when the gain is unity, right? The loop gain becomes unity. So that is, what is the frequency called? The unity loop gain frequency. Sorry. So what I'm going to do is the following. I'm going to check the phase at the unity loop gain frequency. If the absolute value of phase is greater than 180, I can safely say that it's going to be unstable. That's the only thing I'm supposed to do. So let's now take this white Bode plot, white magnitude plot. This is definitely stable for sure. So because if you check the phase here, maybe I'll use what color? This color. At the unity loop gain frequency here, if I check the phase is definitely less than 180. And this difference between minus 180 and the phase where the gain becomes 0 dB, what is that called? You might have heard phase margin, PM or phi m. Just like how PM is important for the country, This PM is also important for stability. So this is basically the phase margin. I'm sure you have seen this before. So again, just to rewrite it, so phase margin is essentially 180 minus the absolute value of the phase at the unity loop gain frequency. And I also know that if my system is unstable, this phase is greater than 180. So what will happen to the phase margin then? That will be less than 0. So if I have a case like this, then I can safely say it is going to be unstable. That's the only thing you are supposed to do. Check the phase where the magnitude becomes unity, and then see if it's less than 180 or greater than 180. Is it clear? So if it is clear, I'll ask this question. So let's say I give you a particular scenario for a particular loop gain, that let us say at some frequency omega x, the phase of the loop gain is 180 minus 180 plus 180, it's okay. I find that the magnitude at the same frequency is, let us say 1000, or let's say maybe not make it, let's say 10. So now tell me if the system is stable or unstable. Unstable. Why?
Because when the gain reduces to 1,
then
the phase will be even more than 1.
Okay. Okay. Let's hold on. Let's put a pin on that. So anyone, any other? Why?
Because we don't know at unity what is the gain.
I mean, at unity gain frequency, we know the gain. What do you want? What we don't know? Phase. I mean, see, remember that what we have to check for stability. At the unity loop gain frequency, what is the phase? That's what we are supposed to find. What is the information given to you? Let us say this is the magnitude, this is phase. The information given to you is at some frequency where the phase is 180. Let us say this is where the 180 degree phase is. The gain is basically some, let us say 10. Now let us say as you increase frequency, maybe you can just, it is safe to assume that the gain drops. I have to check the phase at this point. I know the phase here, but the phase here can either reduce or increase also. That's the same setup we saw here, right? You see here that because of the LHP zeros, the phase was actually increasing. Okay. So you can have a case where the phase is basically dropping also or increasing also. Now if it is increasing, it is going to be stable. If it is dropping, it is unstable. So what should be the correct answer for this question? Yeah, more information is required. That's what you're supposed to ask. It's like the Schrodinger's thing. Unless you open the box, you don't know if it's alive or dead. Same thing. Unless I tell you more information about the system, you cannot say anything. And again, see, if let us say the phase has to drop continuously, do you think it can have left half plane zeros? No. So if let us say the phase is, I'll say phase of the loop gain is dropping monotonically, that is, the phase is continuously reducing, not increasing at all, which means there cannot be any LHP zeros, or I will say that this is an all pole system. So in addition to this constraint, if I tell you that this is an all pole system, then you can say that, hey, because the phase is only going to drop, the phase will definitely cross minus 180, it's going to be unstable. Otherwise, we cannot make any comments. So that's why phase margin is a more stricter constraint than, I will say, gain margin, especially if you have LHP zeros. Because in fact, in practice, there are so many systems for which when the phase is minus 180, the gain can be 1000, 10,000, and still it is stable because of the LHP zeros. And all phase lock loops operate that way, and because of that phase lock loops, you can generate clocks, you can talk on phones. Okay. So anyways, this is now said. So now at least we know that I should look at phase margin, and phase margin must be positive for it to be stable, right? So let us say I give you a case where phase margin is less than 0, and I ask you to tell me where the closed loop poles will be. Where will they be? In the right half of S plane, somewhere here, because it's unstable. If I tell you phase margin is exactly 0, where will the closed loop poles lie? To lie exactly on the j omega axis, because as we saw here, if the closed loop poles are lying on the j omega axis, the at the unity loop gain frequency phase is exactly 180. There is 0 margin. Similarly, if let us say phase margin is positive, but let us say it's a small number, say 3 degrees or 4 degrees, where will the closed loop poles lie? They will be definitely on the LHP, but can you narrow it down further? It will probably lie closer to the j omega axis. So it is not just enough for you to have a positive phase margin, you should have sufficiently positive phase margin. And how much sufficient is again a question that we can debate multiple ways. But there are two limits that can be used in practice. First is the following. So let us say I consider a second order system, for example. If I sketch the root locus here, so let us say the open loop poles are somewhere here. I know the root locus is going to do something like this. Correct? We will not show the arrows here. Yeah. So now you tell me this second order system is stable, but if you are given a choice as to where your closed loop poles must lie on, where will you choose them to lie on? You'll make it lie on the real axis. Now on the real axis, I can have multiple options. Maybe I can have a case where let us say one pole is here, other pole is here, or one pole is here, other pole is here. That is, they can be far apart or close enough. So what might be a preferred choice? Why far apart? Let's say DC gain is fixed now. For a particular DC gain, I am asking where would you want your closed loop poles to be located? Do you want them located far apart or close enough? Why far apart?
One of them will be closer to y-axis and one of the will be very far, so that we can approximate.
This is a closed loop system. Okay, I don't need to approximate at all, right? Think of it like this is a closed loop system. I have two poles which are far apart. So let us say this, I call it as PA and PB, pole A, pole B. Of these two, which is the dominant pole? Low frequency pole is the dominant pole. So which means the settling here will be determined by which pole here? Because this is a low frequency pole, the speed will be determined by this fellow. You want to have faster speed or slower speed? So which means you want this fellow to be at a low frequency or high frequency? You want this to be this way. But if you keep pushing PA this side, what happens to the other pole? That will also try to come here. So what is the optimal point? Both are equal, because after some point what will happen? PA will go here, PB will go here. PB will now become the dominant pole. That will start limiting your settling response. So with respect to the fastest settling you can have, the best case scenario is to have both the closed loop poles lie bang on top of each other. That way none of them is going to dominate. This is the same analogy I give, right? You go to mess with a bunch of friends. If all of them are finishing eating at the same time, that is the best case scenario. If one guy is taking 10 hours to eat, the entire group will wait for 10 hours. And so which means I can say that PA equal to PB is the best case for settling. I'll say fastest settling. And if I have a second order system where the closed loop poles are equal, what kind of damping is that called? Control systems. It turns out it's just a jargon. It's called critically damped. And you can easily show that this corresponds to a phase margin of 76 degree. I'll give it as an exercise practice problem for you to work out. It's pretty easy to work out. Okay. So which means one possibility is you choose a phase margin of 76 degree so that you have the fastest settling in closed loop. So now tell me, if let us say I have my closed loop poles lying in the complex S plane like this, do you think my phase margin is greater than 76 or less than 76? Why? The claim is this corresponds to a phase margin less than 76 degrees. What was the reason? Correct. So, I mean, if the poles are on the S plane, the closed loop settling response, how will it look like? I mean, if they are on the complex S plane, it will show a lot of ringing. If it is showing lot of ringing, do you call it to be more stable or less stable? So logically, the phase margin should be smaller or larger. Phase margin is higher means it is more stable or less stable? More stable. I am saying here that if the closed loop poles are here, I am going to have lot of ringing in the response. So which means it is less stable. So as a result, the phase margin is smaller. So which means if you keep going in this direction, the phase margin reduces. Whereas if I keep going in this direction, what happens to phase margin? Increases. That's a logical explanation. And also, let us say you keep increasing the phase margin, which means one pole moves to a very low frequency, other pole moves to a very high frequency. A limiting case is where the high frequency pole moves to infinity. If one of the poles is at infinity, what is the order of the system? It's a first order system. I had two poles, one went to infinity, so I end up with a first order system. What is the phase margin for a first order system? Why? For a first order system, I just have one pole. At the max, phase can drop to what value? Minus 90 degrees. So which means you have a phase margin of. So the maximum phase margin corresponds to a first order system. Correct. But of course, first order system might not give you the fastest settling. The optimal settling corresponds to a phase margin of 76 degrees for a second order. And then if you keep reducing it further and further, after some point, they will kind of become complex conjugates. So with respect to the time domain transient response, seems like 76 degrees an optimal phase margin to aim for. So this is from the time domain spec. So similarly, now we can try to see what happens in frequency domain. Now remember my closed loop response, closed loop system is this, right? 1 by beta times a loop gain by 1 plus loop gain. Now let us say I try to find the closed loop transfer function evaluated at the unity loop gain frequency. So let me take three cases. Let us say first case where I assume that the phase margin is 90 degrees. If my phase margin is 90 degrees, what can you say about the loop gain at the unity loop gain frequency? This is going to be a real number or a complex number in general? Okay, this is loop gain of j omega, correct? It's going to be real or complex? It's going to be complex, but what can you say about the magnitude at the unity loop gain frequency? I know for a fact magnitude is 1 at unity loop gain frequency. If I say phase is 90, phase margin is 90, what can you say about the phase of the function? Remember my phase margin is essentially 180 minus the phase of this function, correct? So 90 is the phase margin minus 90. So how will I write it now? E power minus j. Yeah. And what is this? E power minus j pi by 2 is how much? Minus 90. Yeah. Minus j. Euler's formula 10 standard max e power I theta is cos theta plus I sin theta. So now I know the value at this frequency. So which means if I try to calculate the closed loop transfer function at the same unity loop gain frequency, this is 1 by beta times minus j by 1 minus j. If I take the magnitude, what does it become? Right. So which means if I try to sketch the closed loop transfer function magnitude alone, this is magnitude of the closed loop transfer function versus frequency. At low frequency this is 1 by beta, and I know that at the unity loop gain frequency this will have a 3 dB drop. In body approximation it's a corner frequency, but the actual thing will have a 3 dB drop. So this again says that for a first order system the unity loop gain frequency is same as the closed loop 3 dB bandwidth, right? Because this is the frequency at which the loop gain becomes unity, the unity loop gain frequency. This, as we are seeing, is exactly equal to the frequency at which the closed loop magnitude response drops by 3 dB. So for a first order system, the closed loop bandwidth is same as the unity gain frequency, the unity loop gain frequency. I'm just redrawing the same thing again. So now let me take a second case. Let's say my phase margin is 45 degree now. So what is the, then can you tell me what is the loop gain? What is the magnitude? Magnitude is 1, the unity loop gain frequency. So loop gain is unity. What is the phase? 135, so minus j 3 pi by 4. And for this value of the loop gain, if you go and substitute here and evaluate the magnitude of the closed loop transfer function, yeah, you can do all that and it turns out it's greater than 1. So basically if my phase margin is 45 degree, you'll have some peaking in the closed loop transfer function. Now limiting case, let us say I take phase margin as 0, then what can you say about the loop gain? The magnitude is 1, what is the phase? Minus 180 e power minus j pi, so this becomes 1 now. So if I substitute minus 1 here, what happens? I mean, this is minus 1 by 1 minus 1 goes to, yeah, okay, minus infinity is what you're trying to say. Okay, magnitude, right? So it's okay. So it blows up to infinity because you're plotting the absolute value, right? So that's it. So which means if I basically keep reducing my phase margin, this is what will happen. I'll have more and more peaking in my closed loop transfer function. So another way to decide what phase margin you might want is to say that I'll choose a particular value of phase margin wherein I don't see any peaking in my closed loop transfer function. Right? So this corresponds to saying that my magnitude at the unity loop gain frequency must be exactly 1 by beta, right? Because I don't want any peaking. I mean, this is basically, I should say it's greater than 1 by beta, sorry. So here it was 3 dB dropping, here it was greater than 1 by beta. If I choose a phase margin for which the magnitude is exactly 1 by beta, then there is no peaking. And you can calculate it the same way we did now. It's a reverse calculation. I'll give it as a practice problem to work out. And it turns out this corresponds to a phase margin of 60 degrees. So whatever calculation we did now, you have to do the reverse, right? Here you calculated what is the closed loop response for a given phase margin. Now you do the reverse and you can work out. So that's why in practice we aim for 76 degree phase margin for fastest settling critically damped response. If that is not possible, at least a 60 degree phase margin is a reasonable thing to do. Okay. Any questions? So the takeaway I want to have is this: for checking stability, only check the phase margin, right? You check what is the phase at the unity loop gain frequency. That's what is crucial. That has to be greater than 0. And for faster settling, you want the closed loop poles to lie bang on top of each other. That corresponds to a critically damped closed loop system with a phase margin of 76 degrees. Again, this you can work out that for 76 degree you have critical damping. I'll give it as a practice set with pointers. Similarly, if I try to sketch the closed loop magnitude response, it turns out if I reduce the phase margin, you see more and more peaking in the closed loop response. So we can choose a particular phase margin where the peaking is not there, and that corresponds to 60 degree phase margin. Okay. So now at least we know some things about stability. Let's try to use this understanding and try to see what will happen to our multi-stage OTA, because that is our prime goal, designing multi-stage OTAs. So let's take a two-stage OTA for example. Let's say this is the first stage. It has an intrinsic output conductance and a capacitance C1, and I have the second stage here. So let us say here I have the intrinsic conductance plus the load conductance. Together I'll call it as GL prime. Here once again I'll have the intrinsic parasitic capacitor plus the load capacitor. Together I'll call it as CL prime. And these are GM1, GM2, two OTAs. And by the way, why did you think I have chosen the input to be given to the negative terminal here? Yeah, remember this is how will you implement this? This is taking one input and amplifying and giving a single output. Simplest way to realize this is how? Common source. What is the gain of a common source amplifier? Minus GM times R0. So to capture that negative sign, I have basically, otherwise at a block level it doesn't make a difference. Okay. So here, where are the poles located at? How many poles are there first of all? 2 poles. Where are the poles located here? G1 by C1 and, let me write it here, GL dash by CL dash. Now remember that in practice my load capacitance can be large, so which means this denominator is going to be large. Now similarly, if I have a multi-stage OTA, the maximum gain is coming from which stage? The first stage is there for providing the gain. So what can you say about the output conductance of the first stage? Output resistance is going to be large. So output conductance is going to be, so you see here this is going to be large, this is going to be small. So it can so happen that these two poles can lie actually close to each other. Right? So which means if I again sketch the root locus quickly. In the open loop, the loop gain has 2 poles which are close to each other. So which means the closed loop poles will do this. But ideally for good settling response, where do you want the closed loop poles to lie on? On real axis, right? So as such, if you take this and put it in feedback, if it has a large enough gain, your closed loop poles might lie somewhere here. I mean on the on the complex plane. So you might have a lot of ring gain. So let's see what we can do to correct that. Let me again copy this. So what we want is the following. My closed loop pole should lie where? On the real axis. Now we also know for a fact that my root locus plot, that is the closed loop poles, they start on the real axis and then branch out to S plane. Correct? So I also know that my closed loop poles start on real axis. So which means if let us say I give you a superpower and say you can position the open loop poles anywhere you want. Right? Now remember I want to have a large DC gain, and for that large DC gain the closed loop poles must lie on the real axis. Correct? So which means if you can choose the location of the open loop poles here, how would you choose them to be located at? You choose them? Yeah, why? I mean, no, remember that I want my closed loop pole to lie on real axis for a large value of DC gain. And I also know that the root locus starts on the real axis and then branch out to infinity. So which means if for large value of DC gain, if I want my closed loop poles to lie on real axis, how would you choose these poles to be? You have to choose them to be far apart. Is that clear? So that they will start on the real axis, they'll be on the real axis for a large values of DC gain, and you are safe. So that is basically one thing you can do. I'll say poles are far apart. I'll say keep poles far apart. So which means if I sketch the root locus corresponding to that, let us say one pole is somewhere here, other pole is somewhere here. Now for even for large values of DC gain, this is going to lie on real axis. Okay. Now I want you to squeeze your memory and tell me, did we see any situation when we discussed poles and zeros, wherein we had poles close to each other, and after we did something, the poles moved far apart? Huh? Yeah, that Miller effect we saw with respect to the common source amplifier. We had a similar setup where without adding that Miller capacitor, the poles were close enough. After adding it, they moved far apart. So same thing can be actually used here for accomplishing this. So because of this is called Miller compensation. And in general, anything that you do to make sure that the closed loop system is remaining stable, that act is called as frequency compensation. So Miller compensation is one way wherein you can do this. So let us say now I don't want to touch my pole locations here. I don't want to change the location of open loop poles because you don't like Miller, for example. But still I want to make sure that my closed loop pole should lie on the real axis. What can we do? No, I mean that is not a reasonable solution, right? So you want to have a large DC gain. For large DC gain, I still want my closed loop poles to fall back on the real axis, but I don't want to touch the poles here. Is there something I can do so that the closed loop poles fall back on the real axis? We already saw if we introduce an LHP zero, the zero will act like a magnet and basically attract this and make it fall on the real axis. So that is something we can do. So second idea is to basically add an LHP zero. So if I sketch the root locus corresponding to that, so the poles are still close enough, but what we are going to do is introduce some LHP zero here. So which means the root locus will basically do this. One will go here, other will go here. So for a large value of DC gain, you are still on the real axis, you are safe. So this act of adding zeros and making it stable is called feed forward compensation. So these are the two schemes that we will discuss in this week. So but now we have just looked at the root locus. Let's also sketch the magnitude plot and see how is it going to look like, the Bode plot. I'll again qualitatively sketch it. So I have to sketch it. Let us say earlier the two poles were close enough. So let us say they were something like this. So this is the magnitude of the loop gain. Similarly, if I plot the phase, it will start from 0, and because of two poles, where will the phase go to? It will asymptotically try to reach minus 180, something like this, right? It will not exactly reach 180, it will try to reach close to 180. So it means now if you check the phase margin without doing anything at this frequency, you see that the phase margin is actually very small. So now when we do Miller compensation, wherein we keep one pole much closer, other pole much farther, what we are essentially doing is this. we keep one pole here, basically keep the other pole here and do something. Just drawn it for rough sketch, not to be taken for this one. If you want to show it clearly, it should probably look like this. So now if I try to sketch the phase plot, due to this low frequency pole, my phase will start from 0 and reach which point? To reach minus 90, and after this the phase will go to minus 1. Now if you look at the phase margin, I have sufficient margin here, so I am safe. So that's how this is happening. Similarly, let's look at what happens in feed forward. So in a feed forward compensation, the idea is you go and introduce an LHP 0, right? So which means I don't touch the poles. The poles are going to be the same, but then here let us say introduce an LHP 0, which means from here it's going to do this. So which means the phase is initially going to drop. After some time it's going to pick up and basically reach minus 90. Again, very rough sketch I am drawing. So which means once again, if you see the phase margin here, it's going to be really large. Very crude sketch, we'll see it in detail when we discuss them. And the other thing to notice is, if you compare either the first Miller compensation or feed forward compensation, when the magnitude plot crosses the unity gain frequency, the unity loop gain frequency, what can you say about the slope here? The slope is minus 20 dB per decade. Similarly here, what is the slope? Minus 20 dB per decade. And what kind of systems exhibit a 20 dB per decade slope? So overall idea is to try to make sure that around the unity loop gain frequency, your system behaves like a first order system. Because one thing we know for a fact is, a first order system is guaranteed to be stable in negative feedback. So you try to make your system mimic a first order system, at least till this point. So again, the lame analogy I give is, this is the stereotypical Indian mindset problem. They'll always, growing up, they'll always compare you with the neighbor's kid, and they'll say, hey, look at Sharmaji's ka beta is doing this, Sharmaji ka beta is doing this, why don't you be like them? No, study like this, do this. Right? So, and try to make you behave like them. So same thing is what we are trying to do. Comparing our system to the first order system, we are trying to do all kinds of things possible to make it look like a first order system, at least till this point. In your case, at least till your exams are over, they'll make you do. So as Indians, we should be expert in frequency compensation. Okay. So one last point for today. So here, when we looked at all this stability, frequency, like location of closed loop poles, etc., we looked at LHP poles and LHP 0, and we know for a fact that if I introduce a left half plane 0, it's going to be good. So let me copy paste this. Oops. Yeah. So we already know if I introduce a left half plane 0, it's going to be good. But the 0 can also be located where? Right half plane. So we should also look at that for completeness. And I mean, we didn't look at RHP poles because that's kind of not the point. So let us say now I have the same case, 2 pole system, but now I have a 0 in the RHP. Let's quickly check the root locus plot. So I have 2 poles, okay, and then I have an RHP 0 located here. So root locus idea is same. It will start from these points. One of them will end here, other will go to infinity. So on the real axis you will have this. So which means this pole goes here, this pole goes here. Now do you think this is good or bad? Why? You see, one pole is actually entering right half plane, right? So which means you are actually well off without doing anything, right? So when you didn't do anything, you had a case like this. You had 2 poles sitting close to each other happily, but making sure that the poles never entered RHP. But in the act of trying to do something and helping the system, if you introduce an RHP 0, that is a huge problem. So this is an RHP 0. So the bottom line, LHP 0 is good for stability. I'll say good. RHP 0, not good. So RHP 0 is like that one friend, in the act of trying to help you, will do something and screw things up and make it even worse. Right? So again, the name, this the depiction I have is this. LHP 0 is like the angel in you, trying to attract you and try to do all the good things and pushing you to the left of plane. Whereas RHP 0 is like the devil in you, trying to tempt you and attract you with all nice things and make you do bad things. So make sure you don't get tempted by this and always go to left of plane. So now let's at least try to understand in time domain why this statement is making sense, that LHP 0 is good and RHP 0 is bad. Okay. We look at that and we'll wrap up for today. For that I'll take a simple case. Let's say I take a simple RC like this. Let's say this is C1. I don't know. So if I apply a step here, what will be if the capacitor is uncharged, if I call this as V out, how will the output voltage look like as a function of time? It's going to grow exponentially. At t equal to 0, it's going to be 0, and then as tends to infinity, this basically reaches this. So this is the time and this is V out. Okay. Now how many poles are here? One pole. Is there a 0 here? No, because if I short this capacitor, the output is 0, so there is no 0. So let's now try to introduce a 0. So let's say I go and add another capacitor here. Let's call this C2. Now do you think I have 0 in the circuit? Because I can short this capacitor C2, my output is still non-zero, I'm going to have 0. Now if this is a circuit, if I apply a step at the input, what can you say about V out at t equal to 0 plus? So do you think the voltage will change instantly or will it remain 0? At 0 plus, do you think it'll voltage will remain at 0 or it can change? When can a capacitor voltage change instantly? If you have impulse current flowing, right? Let us say I didn't have this fellow, old circuit. Can I have impulse current flowing here? Why not? Nothing about resistor being shorted. If let us say impulse current flows here, for example, what can you say about the voltage drop across the resistor? Impulsive. But you see that neither of the voltages are impulsive. So which means we can, by contradiction, we can say there cannot be impulsive currents flowing. So now let us say I have the capacitor put. Now do you think an impulsive current can flow into the capacitor? Let us say, can this current be, I will not show V out, can this current be a delta current? If this current has to be impulsive, this current cannot be impulsive, which means the impulsive current has to flow here. Now can impulse current flow through the capacitor C2? If impulse current flows through the capacitor C2, what happens to the voltage across capacitor? Voltage is integral of current, so this will step up. Now you see there is no inconsistency, all the voltages are stepping up, correct? So again, impulse current is like a huge spike of current. When you have a huge spike of current, where will that current tend to flow? Here or here? Through the capacitor. So at t equal to 0 plus, you can loosely say that the resistor is not active. So which means you have a situation like this. So what will happen to the voltage now? Now you have a circuit that looks like this, correct? So you have a input voltage and 2 capacitors. So what is the output now? It's voltage division between C1, C2, and what will be the divided value? It will jump up instantly. So C2 by, is that okay? Now of course, after time progresses, this will again slowly charge. Basically. Is that clear? I mean, if you want to speak in very layman terms, you can say at t equal to 0 plus, what do you say for capacitor? Acts like a short circuit. So this also acts like a short circuit, this also acts like a short circuit. So you'll have voltage division happening between these two short circuits. That's all. That's a very layman term to look at it. And as t tends to infinity, capacitor is open. So no DC current flows through the capacitor, you know that. So which means this should get charged to 1 volt. Okay. So now here, let's quickly find the location of 0, right? How will you find the location of 0 here? Yeah, let's assume that V out of S is 0, and yeah, you basically apply KCL here. Some of these two currents are 0. If this is, let me call it as V in of S. What is the current flowing through the capacitor C2? So let me write it here. V in of S times SC2 plus the current through the resistor here, that is V in of S. Sum of these two currents must be equal to, so I know V in of S is non-zero because I am applying a non-zero input. So this results in a location, 0 location, and this is located in the left half plane or right half plane? So as you see here, if you have a left half plane 0, then you apply a step jump here, the output instantly rises in the same direction as you want your final output to reach. So in a way I can say that the 0 is helping you reach the output slightly faster, or I would say this is giving some kind of a time advance, right? Basically if you have to extrapolate it, it looks like the kind of starts before you apply the input also, but that's not what happens, but you can sort of think of it like that. And remember that when you have poles in your system, whenever you have a pole in a system, you have a delay in the system, right? Because pole is arising due to capacitors. You need to have finite time to charge and discharge capacitors, so you have delay in the system. And anytime you have a lot of delay in a negative feedback system, so let's say this is your negative feedback system. If you have one pole, there is going to be some delay. If you have more and more poles, you'll have more and more delay. And anytime you have more and more delay in a negative feedback system, what can happen? Yeah, I mean, let's say you have a lot of delay in the negative feedback system. What can happen because of a lot of delay? I mean, even fundamentally, forget about settling. I mean, the simple example I give is, let us say you want to take bath in warm water during winter time. You have two taps, one cold water, one hot water. You open both the taps and keep the bucket. So ideally what you do, you open both of them, you dip the hand in the bucket and check if the temperature is fine. Depending on that, you basically adjust it. If you are doing it fine, the temperature reaches the correct value. Now let us say you are doing it very slow. In slow motion you are doing this, right? So which means there is a lot of delay in your sense and feedback path, right? So there is a lot of delay in the loop. So let us say the water is actually initially cold. It started to increase. Now you dip the hand and then take it out, and there is a slow action there. Now what will happen? By the time you try to correct something, water temperature would have increased. So although water temperature would have reached the correct point, you acted slowly. So you will think that the temperature is very high. So what you will do now, you will reduce hot water, increase the cold water. Now again the temperature will try to reduce. Now once again, if you do it very slowly, you will try to think that the water has become colder, and then you will go like this. Now if you are doing it sufficiently fast, maybe you will settle. If you do it really slow, you lost it. It may, I don't know, it may even grow unbounded, right? I mean, yeah, right? So which means anytime you have a lot of delay in a negative feedback system, what can you say about the overall closed loop system? It can become unstable. That is why when you have more and more poles, you have more and more delay, it can become more and more unstable. Now, as you see here, the moment you have an LHP 0, it seems like there is some kind of a time advance, because the moment you have LHP 0, the output steps up in the correct direction from the start itself. In a way, LHP 0, I will say, introduces a time advance that counters the delay due to poles. So that is why when you introduced an LHP 0, we see that it is kind of becoming more stable, right? We saw here with the root locus plot. That's other way to look at it. Okay. Now let's quickly check for RHP 0 and we'll wrap up, right? So let's say the same point, the same circuit, I have to make the 0 move to RHP. What should I change here? Here I had an LHP 0 because of this calculation, let us say. Here I want this to become plus. What should change? Sorry? As of now, this is minus, right? Solution of this is minus 1 by RC2. Let us say I want to make it plus 1 by RC2. What should change here? If this has to become plus, both terms can they be of the same signs? One of them has to be negative, other has to be positive. So which means the simplest way to make it RHP 0 is change the sign in one of the parts. So let us say I say that I go and give inverted, right? So if you do this, now we can clearly see, right? So if I have a case like this and I apply an input step at 0 plus, what will happen? Once again, remember, you will have voltage division happening between these two fellows, but to what value will the voltage jump to? The same value but at minus. So basically this will go negative, and then this will take more time. So if you have an RHP 0 like this, you see that at 0 plus, the output goes in the opposite direction to where you actually finally want to reach to, which means this introduces more delay in your system, right? So if LHP 0 introduces time advance, I would say RHP 0 adds time delay, and that is why you get a situation where the system can become more unstable. Okay. So this is like asking someone, how to reach, from point A to point B, and that guy asks you to go in the opposite direction and makes you go all around, introducing the delay. Same thing is happening here. So we'll stop here and we can continue. I think already I had announced tomorrow we'll have a class at 6 p.m. we'll start in same class. I'll put out a mail also.